Hello everyone, and welcome to the Mechanical Engineer Essential channel. I'm Mohammad Reza Teimouri, a mechanical engineer, and in this video, we're continuing with part 8 of our ANSYS Fluent tutorial series. In this part, we'll be focusing on post-processing, an essential step where we analyze and visualize our simulation results. We'll start by using CFD-Post. From the top menu, go to the Locations tab and select Isosurface. An isosurface is a very useful tool that helps us slice through our domain to observe variables on a constant surface. Let's name this new surface XZ plane, since it will represent a plane that cuts through the domain along the X and Z directions. Now in the Geometry tab below, we set the variable to Y, which tells the software that we want this surface to be placed at a specific Y location. We select Hybrid for boundary data, which gives us a more balanced and accurate interpolation, especially when dealing with mixed meshes. We then set the value to 9, meaning the surface will be created at y equals 9 units. This defines the exact location of our cut and helps us focus our analysis on that specific slice. These settings help us extract detailed information from the simulation and are the first step in understanding flow behavior inside the domain. Next, let's move on to the Color tab in the Isosurface settings. In the Mode section, we set it to Variable. This means the surface will be colored based on the distribution of a physical quantity, giving us visual insight into how that variable behaves across the plane. We select Temperature as the variable. This is essential in thermal fluid simulations, as temperature distribution helps us detect hot and cold zones, assess heat transfer, and understand the efficiency of thermal designs. Now, let's go to the Render section. Here are the visual configuration settings we'll use. Transparency enables us to partially see through the isosurface, which is especially useful when we want to visualize inner flow structures or other geometries behind the surface. Draw mode, we set it to Smooth Shadowing. This option enhances the surface appearance by applying soft shading, making the gradient of the temperature more visually intuitive and smooth. Face culling. We choose no culling, meaning both sides of the surface are rendered. This ensures full visibility of the surface regardless of which direction we're viewing it from. Lastly, we uncheck the lighting option. Disabling lighting removes artificial shadows, ensuring that the colors represent only the variable's magnitude, not external shading effects. This leads to clearer and more accurate visualization of the data. Now let's create a new isosurface in the Location tab. We'll name this new surface Gas. This surface is meant to help us visualize the spread of carbon dioxide in our domain. In the Details section under Geometry, we set the variable to CO2 mass fraction. This means we're focusing on the concentration of carbon dioxide in the flow field. Next, we set the value to 0.001. This defines the exact isosurface level. Any location in the domain where the CO2 concentration is 0.001 or 0.1% will be included in the surface. This helps us detect regions where combustion gases like CO2 start to appear or concentrate, which is especially useful in combustion or exhaust simulations. Now we move to the Color tab. We set the mode to Constant. This makes the surface appear in a single solid color, rather than being colored by a variable. Why do we use constant color here? Because we are only interested in the shape and location of the gas boundary at a certain CO2 level, not its gradient or variation. Next, let's go to the Render tab. We'll use the same settings as before. Draw mode, Smooth Shadowing adds a nice visual shading for better surface visibility. Face culling, no culling, ensures both front and back sides of the surface are visible. Transparency, this can remain unchecked, since we want to clearly see the boundary. Now, we enable two options. Lighting, this adds realistic shading to the surface, helping it visually stand out with depth and dimension. Specular, this introduces a shiny reflection effect. When light hits the surface, you get highlights, making the surface look more realistic and easier to distinguish from the background. These visual enhancements help us better interpret the location and spread of combustion gases in the domain. Now we're going to add a streamline to visualize the flow path of the fluid. Go to the top menu bar and click on Streamline. We'll name it simply Streamline to keep things clear and organized. In the Details section, first we set Start from to Inlet_Exhaust. This means the streamlines will originate from the inlet boundary, allowing us to track how the flow moves through the domain starting from where the exhaust gases enter. Next, we set number of points to 100. This controls how many seed points are used to generate the streamlines. A value like 100 ensures a dense and smooth distribution, giving us a more detailed and continuous visual of the flow. Under the direction setting, we choose backward. This may sound counterintuitive, but it tells CFD-Post to trace the flow lines in the reverse direction, starting from the inlet and moving backward along the velocity field. In some setups, this helps visualize recirculation zones or reverse flow behaviors, especially important in combustion and exhaust simulations. Now let's move to the Color tab. We set the mode to Variable, and we choose Temperature as the variable. This colors the streamlines based on the local temperature at each point along the flow. It allows us to not only see the path of flow, but also understand how temperature changes along that path. Then, under the Range section, we switch to User Specified. This gives us manual control over the coloring range. We set the minimum to 300K and the maximum to 400K. By defining this range, we can focus on subtle temperature differences in that specific interval, which is especially useful when analyzing low to mid-range thermal variations within the flow. Finally, we click Apply to generate and display the streamlines with the settings we've defined. These streamlines are now a powerful tool to help us track the fluid motion, temperature distribution, and potentially identify hotspots or cooling zones within the system. Now that our streamline visualization is complete, we'll turn off some of the previous displays to keep our view clean. In the object tree on the left side, simply uncheck both gas and streamline. This will hide the isosurface and the streamline, making space for our next visualization. Next, from the top menu bar, click on Volume Rendering. We'll name this new object Gas Volume. In the Details section at the bottom of the screen, locate the variable setting and choose CO2 Mass Fraction. This setting will visualize the volumetric distribution of CO2 inside the domain. Unlike isosurfaces or streamlines, volume rendering displays a smooth, 3D gradient of the selected variable through the entire volume. It helps us see how CO2 is spreading and accumulating throughout the domain, not just at a surface or along a line. Finally, click Apply to generate the volume rendering. This visualization allows for a comprehensive look at the gas dispersion behavior inside the system, and is especially useful for understanding mixing, combustion efficiency, and pollutant concentration zones. Now that we've completed the main steps of post-processing in CFD-Post, including creating isosurfaces, volume renderings, streamlines, and setting up color maps, let's take a brief look at some additional powerful features that CFD-Post offers to enhance your analysis and reporting workflow. In this part, we introduced animations to visualize how the flow evolves over time, expressions and functions to define custom calculations using field variables, charts and tables to extract and graph data from lines, points, or surfaces. Automatic report generation for compiling simulation results into ready-to-share documentation. Multiple case comparison to analyze design variations side by side for better decision-making. These features are especially helpful when working on complex fluid systems or presenting your findings in a clear and visual format. To wrap up, go to File, quit in CFD-Post, and don't forget to save your project from the ANSYS Workbench project page so none of your work is lost. And that brings us to the end of this part and the completion of the entire project. In this session, we covered the final post-processing steps in CFD-Post, including creating isosurfaces to visualize planes inside the domain, adding streamlines to show the flow pattern of gases, using volume rendering to highlight the CO2 distribution in the domain, and exploring additional features like animations, custom expressions, charts, and automatic report generation. Through this project, we went from geometry creation, meshing, setting boundary and solver conditions, running the simulation, and finally to interpreting and visualizing the results, all within ANSYS Fluent and CFD-Post. This marks the completion of our current simulation project. In the next session, we will start a brand new project with fresh challenges and techniques, so make sure to subscribe, like, and turn on notifications so you don't miss it. This is Mohammad Reza Teimouri, Mechanical Engineer, and you're watching Mechanical Engineer Essential. See you in the next project.